Hello, and welcome to this session. Today we're going to look at Texas Instruments STEM projects, and we're going to focus on our TI Innovator rover. I'm Beth Smith, and I'm an education technology consultant with Texas Instruments. Prior to that, I taught math for 25 years. The subjects anywhere from pre-algebra through pre-calculus and probability and statistics. I was also a T-Cube instructor and a math coach for Texas Instruments as well. So I'm excited to work with you guys. If you have any questions, feel free to email me, bethsmith@ti.com, and also follow me on Twitter at bismith15. So let's get started. First, we'll talk about why coding and where this fits into the math curriculum and other areas as well. I'll give you a brief overview of TI's coding and STEM program and an overview of our TI Innovator rover. Next, we'll look at a couple of our activities. First will be Drive the Line, which does a great job of connecting distance, rate, and time from both a math and a science perspective and helps the students develop an understanding of slope as a rate of change. After this, we'll look at Two Rovers Leave the Station. Here, students investigate the intersection of two lines, and in this case, where the rovers will meet. And again, it helps the students develop a solid understanding of slope as the rate of change. So let's get started. I think this quote by Steve Jobs is a great place for us to start. Everybody in this country should learn how to program a computer because it teaches you how to think. As educators, we all want our students' brains to grow. We want them to get smarter. We want to help prepare them for the future. Coding can help us accomplish this. Your students are going to solve problems, they're going to struggle, they're going to learn how to persevere, and they're going to learn procedural fluency. They have to know step by step where they need to be and how are they going to get there. It helps them reason abstractly, and we can do this through modeling. They're also paying attention to precision. For example, if they're going to have the rover turn, there's a big difference between turning 30 degrees and turning 40 degrees. And also, it's going to help prepare them for the future, whether that's a college career or a technical career or some other type of career. A lot of what they are going to face, they're going to have to understand the language behind coding. I want you to think about embedding coding into your curriculum. So it's not extra, it's taking the place of some of your curriculum. For instance, the concept is as if you can code it, then you know it. So perhaps have your students program the rover to draw around Mars, and it shows their understanding of the coordinate system. Or perhaps have them code the rover to draw a trapezoid, and you can give them certain parameters so that they understand the properties of a trapezoid. They can develop a conceptual understanding and derive formulas. As they program the rover to drive a triangle, a square, a pentagon, they're discovering that the exterior angles add up to be 360 degrees. And they're deriving the formula for the sum of the interior angles of a polygon. That's going to help them answer the why behind the how. So we're just not putting a formula up on the board. And you can use this as an alternative assessment. I'd like to give a quick overview of our STEM program, and then I will go over some links with you all at the end of this session. First, we have 10 minutes of code, which can be done as a group activity, or students can do these individually and work through them at their own pace, so every student is experiencing their own level of success. We also have a lot of teachers who like to work through these that may be new to coding. The units are broken down into skill builders, and each skill builders are broken down into steps where the students see what code they're actually putting in, why they're putting in this code, what it means, and then a screenshot of the graphing calculator right next to it. And at the end of each unit, there's an application where they do a mini project. We have math and science and motion activities, and there's no coding experience required to work through any of these activities. Last, we have STEM projects that are just awesome. Students can go through and work through our projects, and the hope would be is after they complete some of these, they identify a problem in their environment and use coding to solve this problem. This picture is showing our pet alarm car that was actually developed by a middle school student for a science project. So what TI equipment do you need to start using the rover with your students? While we can code on any of our graphing calculators, in order to use the rover, we need either the TI Nspire CX, the TI Nspire CX2, or the TI-84 Plus CE. The graphing calculators talk to the hub, which is a microcontroller. Think of that as the brain. And then the hub is placed inside the rover. Let's take a look at this. So this is our hub. We have inputs and outputs that can be used for probes, servo motors, and many other things. On one end, we have a brightness sensor. On the other end, we have a mini breadboard. And on the bottom, we have a sound card. So you can imagine everything we can accomplish with this little guy. Let's take a look at some of the features of the rover. You can put an expo pin in it, and so it's going to draw whatever is programmed in there, which is great for geometric figures. At the back underneath is where the hub is located, our brain. At the front are our motion sensors, so think of the CBR2. And on the bottom is where a colored sensor is. At the rover specs. The language that we use is TI Basic. We will be coming out with Python this fall that will be available on the TI Nspire CX2. It's menu-driven coding, which is great for students that are brand new to coding or those that perhaps have had experience with drag and drop. 1 unit is 1 decimeter or 10 centimeters. The default distance is 1 meter or 100 centimeters. And the default speed is 0.2 meters per second or 2 centimeters per second. The rover will accept speeds between 1.4 and 2.3 centimeters per second, which becomes important as we do some activities. And the default angle is 90 degrees. First activity, Drive the Line Challenge. I like to think of this as math and science in motion because it really is a great activity to do in math and science classes, or perhaps even together. And I think it's appropriate for middle school all the way through high school, and then you could just adjust it depending on where your students are in the curriculum. The students are able to explore representations of position, time, speed, velocity, as they're going to write the code to navigate through challenges. And I like to begin by talking about what slope is, and so feel free from here on out to pause the video as need be, because there's a lot of different ways to look at slope. I like to make sure that we include that it is a rate of change, that it's the change in the vertical over the change in horizontal, and that it can be positive, negative, 0, or even undefined. This activity also does a great job for students to begin to understand the similarity and differences between velocity. And again, I think that we can begin this discussion in middle school as well. And if we can, think about how much better prepared they're going to be as they get into high school and some of the upper level classes. So again, just pause and take a look at how we look at speed and velocity and perhaps what you could add. So let's look to see where we can locate this activity on our website and download this. So if you go to education.ti.com, I'm going to go to activities, and keep in mind there's other ways to get to this activity. I'm going to go to TI Innovator Lessons. I'm going to scroll down until I see Math in Motion and click Learn More. So we have Math in Motion activities, which is where the students are required to do some coding, and Math in Motion activities where the students simply run a program. So the first activity we're going to do is from Math in Motion Plus, and we're going to do Drive the Line Challenge. And so since we're using the Nspire today, I'm going to click on the TI Nspire activity files. And that's basically going to download all the activities wherever you send your downloads to. And it comes in a zip file. And if I open this and look at this, what you can see is that it's unzipped it. And if I open this file, I have my TI Nspire CX files. We have the student activities that you can print out that come in PDF or document form, and also the teacher notes. And I love the document forms because a lot of times I may edit them just to suit the needs. And that's actually what I've done with this activity a little bit, and I'm happy to share that with you. And then you also have the TNS file that you need to put on the students' Nspires. And so let's look at how you do that now. So I've opened up my teacher software for the TI Nspire Premium Edition. And if you have the Navigator system, then you would just send it to your class. You may have experience to do that, but let's say you don't. So right now you can look under Content tab and see that I have one handheld connected right here. So I can go to Tools, and then I'm going to go to Transfer Tool. I'm going to click Add to Transfer List. And I went ahead and found my Drive the Line TNS file in my downloads. I'm going to click Select. You can choose to keep the folder the same. It's going to go into whatever the date is, but in this case, I'm going to rename it Camped. And click Change. And then you can see that right there. And then I'm just going to click Start Transfer. And this is really, really quick. So I now have that on my handheld. So now that we have the background information as far as what this activity is about, and we've downloaded the TNS file to our Nspire, let's look at how this could look in the classroom. So the first thing that we're going to do is to write a pretty simple program that will help us learn how to drive the rover. And so to start a new program, I'm going to go to my home key, and I want option 1 for new document. Lots of ways to do it. I choose just to select the number 1. And if it does ask you to save a document, simply say no the majority of the time. And we want number 9. We want to add a programming page. And I'm going to click New. And let's just go ahead and title this Motion. And I'm going to click OK. So as you can see, we have our programming page, and it already does this for us to put where our program is going to begin and our program is going to end. So when we are doing activity with the rover, the first thing that we have to do is we have to tell the calculator to talk to our hub and our hub to talk to the rover. So I mentioned that everything is menu driven. So I'm going to press Menu, and I want, hey hub, let's talk to our rover. And let's first connect our rover. So it was Menu, Hub, Rover, Connect Rover. Now you can see that we have our first line of command. Something that's very, very important is every time we put a new command on the calculator, we have to press enter because every command needs to start on its own line. Now for this activity, what we want the rover to do is we want to first have it drive forward at a rate of 2.3 units per second for a time of 3 seconds. And so think about the questions that you could ask. Again, we can pause the video. So basically, the rover is going to travel a total distance of 6.9 units, and it's going to travel for 3 seconds. And this is going to become important because once we have the students write this program and drive the rover, we're going to ask them what this would look like on the coordinate plane. So from here, we're going to go Menu. And again, we want the hub, number 8, to talk to our rover, number 7. And now we want to drive the rover. So we want it to go forward, and we want it to go to a certain speed. So we have to go back and grab that speed. So we're going to go to Menu, again, 8 for Hub, 7 for Rover, and then we want Rover Settings. Now, let's say that you weren't really sure to go and you press Drive Rover again. To back out of that menu, it's the same concept of what's on the computer. We're going to go, let's escape out of that. And then I remember, oh yes, it's actually in Rover Settings. And then speed. We're going to type in 2.3. Then we need the time. So again, I'm going to go to Menu, 8 for Hub, 7 for Rover. I want RV Settings, and I want time. Now, if you notice what happened over here, it automatically put these spaces in for us. And I'm going to press 3. Again, I'm at the end of my code, my command, so I'm going to press Enter again. Our next 2 steps, we want the rover to now stay for 3 seconds. So we want time to keep going, but the distance is going to be 0. So to tell the rover to stay for 3 seconds, we're going to press Menu, 8 for Hub, 7 for Rover, and then in a sense this is Drive, even though we're not going anywhere. And you can see that number 7 is Stay. And we press Enter, and we're going to stay for 3 seconds. And again, that's our command, so we press Enter. Now we want the rover to drive backwards 3 units at a rate of 1.5 units per second. So let's think about it. So a couple of the questions that we could ask the students would be, okay, well, how far is it going to travel? So 3 should be pretty easy for them. But then you have to think about, well, how many seconds then? And so they would have to deduct and do a little bit of math to say, okay, so 3 divided by 1.5 is going to be 2 seconds. So we're going to go Menu, 8 for Hub, 7 for Rover. We're going to now go drive the rover backwards. So number 2. And we want to do that for 3 seconds. At a speed of 1.5 units per second. So we're going to go Menu, Hub, Rover, Speed, which is in RV Settings, for a speed of 1.5. Now we are through with our program. When you run a program, you run a program on a calculator page, but we first have to save it and check for syntax. So if I press Menu, and we can see number 2 is check syntax and store, we have a couple different options. We can check the syntax and store it. We can just check the syntax, or we can go ahead, check the syntax, store it, and run the program. Notice the keyboard shortcuts. So I'm on a Mac, so that's why it says Command R. But if you're on a handheld, if you go Control R, and that's a great shortcut that you're going to want to remember. What that's going to do, I'm going to back out of this just for a second so you can see. If I go Control R, it saved it. And if you notice, it inserted the calculator page. And it's like, okay, go ahead and press Enter if you're ready to run this program. So let's test this out. on the floor, and where you see my hand is where you want to line up the starting point at the end of the motion sensors. I've pressed enter. You can see it go forward, and then it stays, and then we're going to go backwards. Notice the difference in speeds. So the next step would be to make the connections between what the rover actually did as we drove it, and how does that translate to that graph of distance versus time, which so many students struggle with. So the goal would be to have the students basically graph what the rover did on that horizontal line. So if we look at what that should look like, we know that the rover drove at a speed of 2.3 units per second for a time of 3 seconds, so that the time would be 3 and the distance would be 6.9. Then we stayed put for 3 seconds, so on the coordinate plane we're at 6, 6.9. We then had the rover travel backwards 3 units at a speed of 1.5 units per second. So that meant that this took 2 seconds, so we're at a total of 8 seconds, and then basically it drove backwards the 3 units. So you can see how the students can really make a connection between the verbal description, what the coding looks like, and what that looks like on the coordinate plane. The next part of this activity has the students really do the reverse of what we did before. So they're given graphs and they're supposed to write programs that would have the rover drive this path. Now keep in mind, when they drive the rover, they're driving it along that number line. So they're driving it along a horizontal axis. And then what the program does is it will transfer that to the coordinate plane. Let me show you how that's going to work. So let's say that they were going to do challenge 1. So this is an example. This would be your challenge 1. So they would go to page 1.2, and again, there are handouts for this. This is the graph that they're going to try to drive. On page 1.3, they would then write the program for that graph. They would go and run it on page 1.4. And if we look on that page what the different programs are that they can run, I press the variable key in case y'all did not see that. They would run challenge 1, which is what they wrote, and then they would run a program called challenge 1 check. And don't forget, after you select a program to run, you want to press enter to actually run that. After they ran their program, challenge 1, and then they go back and run the challenge 1 check, it will just say done, but they go back to the graph page, and in red it will actually plot on top what the rover actually drove. And so this is awesome, because if the students did not get part of it right, they can troubleshoot based on what they programmed the rover to do and what it actually did. So let's get started with this challenge 2. And so I have the activity, the TNS file that I showed you guys how to put onto the calculators, called Drive the Line. And challenge 2 begins on page 2.3. And I went ahead and coded this for us so we wouldn't have to take that time. And this will be something for you guys to pause and see if you can go back and do on your own. And one thing I didn't mention in the first part is keep in mind there's always at least a couple ways to perhaps have the rover drive the way you want it to. And so if we look at this first part right here, we can see that because we have a positive slope, that the rover is going to drive forward. And it's going to drive forward for a total of 3 seconds. and it's going to travel 6 units during that time. And so what I chose to do is just to have the rover drive forward at a speed of 2 units per second for a time of 3 seconds, which would give us what we need. Then when we look at the second part, we can tell that since the graph is negative, that the rover is going to drive backwards. And we're actually going for a total of 5 seconds. And we're basically going to go from +6 all the way down to -4. So we've got to go a total of 10 units. And so again, I chose to have the rover go backwards for a total of 10 units and to take 5 seconds to do that. So that was just a different way that we could write that. When we're ready to run this, remember we press Control and then R. That checks for syntax, saves it, and throws it on to that next page. And so with our rover on, we would press Enter, and it would run that challenge and then show done when it's through. After this, we would press our variable key, and then that's where we would run the challenge check, and then press Enter. Now keep in mind, you're not really going to see anything on the calculator on top of the rover, as you'll see when I show the video. But what you can do after that point is then we will go back to that page 2.2 and you'll see the red line. Enter. And then here we're going forward, so going up the graph, and then we're going to go backwards with that negative slope. And then what we want to do is press our challenge check like we talked about, and then go back and press Enter to have it run that. Go back to page 2.2, and we can see that that red line is pretty close to blue. The second activity we're going to look at is also from Math in Motion, and this is another one of my favorites. So again, from our home site, I'm going to go to Activities and then down to TI Innovator Lessons, and then I'm going to scroll down to Math in Motion, and we're going to go to Math in Motion since this is not one that the students are going to have to code. They're just going to input some values in a program that's already written. And we're going to scroll down to 2 rovers leave the station. And so this is just a great alternative to that problem in our algebra books where we're talking about trains or cars, where the students may not really have a clear picture of what's going on. So it really investigates where the 2 rivers are going to crash and what that would look like as a point of intersection on the graph, and does an awesome job of connecting slope to velocity. And so you would click here and download the activities just like we did the last time, and open up the TNS file, and I've already done that, so we can go from there. As I mentioned, the students will use a file that's already programmed for them, and they're going to illustrate the intersection of 2 lines by having the rovers crash into each other. The crash is going to use the horizontal distance from the origin as S of t as a dependent variable, and then time t as the independent variable. And it's just important for the students to understand that velocity is the slope, and this activity does a great job of making that connection. It also does a great job of getting them to understand that the y-intercept is the starting distance from the origin, or the initial position. The first task for the students is to look at the functions s of t equals 2t minus 4 and s of t equals negative 1.5t plus 10. First, they want to solve these algebraically using paper and pencil, and then they can graph them by hand as well. And they could check them on the TI Inspire. They could check this graphically, and then they could also check this using the algebra menu as well. It's important to have the students discuss the meaning of the slope and the y-intercepts so that they learn to understand the slope is the velocity and the y-intercept is the starting point of the rover. So the point of intersection is 4, 4, which means that the rovers will crash at 40 centimeters after 4 seconds. And let's keep in mind that 1 unit represents 10 centimeters. So let's look at how you could solve this on the Inspire first. So I have a calculator page opened up. I'm going to go to Menu, Algebra, Solve Systems, and you can basically put whatever variables you'd like to, but just to keep it simple today, I'm just going to use the variables x and y. Then we want to click OK, and keep in mind that you can put these equations in any form you want to, whether it's standard, y-intercept, or any other form. So we're going to go ahead and type in y equals 2x minus 4, and arrow down, and then negative y equals negative 1.5x plus 10. And then we can press enter and solve. So we can see that they intersect at 4, 4. I've got a graph page opened up. So in F1, I'm going to type in 2x minus 4. We can arrow down to type in the second function. And so we're going to type in negative 1.5x plus 10 and press enter. So I'm going to move that second function out of the way so we can see that point of intersection just a little bit better. And what's nice, especially for some of the younger students, is to put that grid behind there, which is what I'm going to do this time since we have some nice clean numbers and really look at a different way to find the point of intersection. So we can see that it's at 4.4, but let's verify that. So we can actually go to Trace and go to Trace All. And we can use our right arrow to see if we can't capture that. Notice that the points, the ordered pair is in the bottom right corner. So we can't capture it, but we can type in the number 4 and press enter. And you can see that it's verified that both of those functions are 4, 4 at that point. There's other ways to find the intersection point. I just thought that this was a nice way to look at it given the problem that we had.